Good morning, everyone. Welcome to the SDVoE booth here on the second day of InfoComm 2018. My name is Helgi Sigurðsson. I'm a product manager with Semtech, one of the founding members of the SDVoE Alliance. And today we are going to be talking about the ugly truth of video over 1 gigabit Ethernet. So for many years we have been talking about this AV and IT convergence. Control moved over to the Ethernet many years ago, long before I joined this industry. Audio has moved to Ethernet very rapidly over the last several years. And at the same time, video over Ethernet, there has been some effort in moving video over the Ethernet hardware as well. So why is it that, how come not just all AV distribution today has made the leap big time to this? And it turns out it's not per se bandwidth that is the problem. The problem is shared bandwidth. The issue is that when you start putting AV onto 1 gigabit infrastructure, you make compromises. Compromises that you don't see in a regular matrix source. And on top of that, AV over 1 gigabit starts consuming a large portion of this infrastructure. And there's just not enough space on this infrastructure for IT and AV living together. Because remember, AV and IT convergence is all about having AV and IT on a single infrastructure in harmony, not affecting each other. So what's the reason for that? Well, the reason is really the video itself. Video requires a ton of bandwidth. If I take HDMI signal, I remove all the overhead from the HDMI signal itself and then extract just the native video information from that signal, I have a raw video bandwidth of somewhere between 2 to 12 gigabits per second. To take that bandwidth and put it onto a 1 gigabit network link, it means compression. And it means a lot of compression. Before I go and talk about compression, I need to get a few definitions out of the way here. First is the codec. Codec is typically a pair of algorithms, the encoder and the decoder. What these encoder and decoder do is basically take the native signal, convert it into network bits, and then they take these network bits and convert them back into the original signal. When compression is required, the compression itself is integrated into the codec itself. Here we are going to be talking about video codecs. Audio codecs exist of two, but because video and audio are two very different signals, audio codecs and video codecs are very different too. Next definition is bandwidth. So what is bandwidth? So the codec puts data out onto the network, and that is your bandwidth. Bandwidth is measured in megabits per second or gigabit per second. And bandwidth is actually something that follows the Moore curve. Bandwidth is cheap today and is getting cheaper every year. If you go into a data center today, you will find out that the data center has already converted over to 100 gigabit infrastructure. And actually this year they have started testing 400 gigabit network switches. Next definition is latency. Latency is time. What time? Basically the time from the image leaving the source until that same image is presented on screen. The total latency is the sum of the transport time itself and the time it takes the codec to translate these signals into network data and back into the original signals. Transport in a standard network system is always under 1 millisecond. However, codec time can be typically 100 milliseconds. There was, a few years ago, a research study done by a university in England, who was actually looking at what is the effect of latency on the regular computer user. And it found that computer operators become affected by latency once latency becomes more than 50 milliseconds. Finally, quality. Quality is easy to understand. It's the image what you see. It's basically what is the difference between the image on screen compared to the original image leaving the source. Quality, like you say, you see it, but it can be quantified with tools and algorithms. SSIM is a particular metric which is very common to use, because that one in particular takes into account how humans perceive quality. So now it comes back to compression. When you compress a video signal, you generate artifacts. As you compress more, these artifacts become visible. Furthermore, as you compress more and more, compression algorithms have to start make some assumption about the image itself. As you know, desktop images, synthetic images, and natural scene coming from a camera have very different structure. And since when you start compressing a lot, you can optimize for one or the other. You cannot optimize for both types of images. Therefore, when you start compressing a lot, you will start getting different artifacts on synthetic images, so computer graphics, versus natural scenes coming from a live camera. Compression also becomes very, very problematic when the goal is to take this signal and display it on large-scale displays where everything gets magnified. So now those little artifacts that were barely visible on a 24-inch monitor, they become really, really visible on a 10-meter tall screen. Therefore, in these kinds of applications, you have to avoid compression. And this leads us to the codec triangle. Latency, the codec itself creates a trade-off between latency, bandwidth, and quality. And as every optimization problem like this, you can only optimize for 2 out of the 3. So you can, for example, decide that you want to optimize for low bandwidth and high quality. What now happens is that you have to use a more sophisticated compression algorithms that takes longer time, and therefore your latency goes up. You can instead, of course, optimize for low bandwidth and low latency, but now your quality of the image will suffer. And you can say, okay, bandwidth follows the Moore law. Bandwidth is already cheap, it's getting cheaper. We are getting more and more bandwidth every year. So I can instead say, I want to optimize for high quality and low latency. So this is like the performance of the matrix switch. But now you have to sacrifice the bandwidth. Typically, when it comes to compression algorithms, there are 2 different classes of compression algorithms. First is what we call the Intraframe codec. This is very easy to understand. This codec will take this video, will break it up into frames, and then analyze and compress each and every frame independently of the other frames. Basically, it's really like JPEG or JPEG 2000 compression, but done now on sequence of frames, one after another. So therefore it's called Motion JPEG or Motion JPEG 2000. And this is where we get in problem with the 1 gigabit infrastructure in particular. Because in order to if you do this kind of a compression, you still end up with visible artifacts. They may be small, but they're still visible. you still end up with latency. Yeah, it may be small, but it's typically always 50 to 100 milliseconds. And on top of that, in order to just get there to this quality with small artifacts and small latency, but still latency, you have a bandwidth that is taking up hundreds of megabits. So if you're working on a 1 gigabit network, you are now choking the IT user if this is on a converged infrastructure. The solution to this, of course, and what happens is that people start deploying this as two independent infrastructure, AV system and an IT system. The other type of a codec is the Intraframe codec. These are very, very efficient codecs. What they do, instead of taking one frame at a time and compress it and send it out, they take together several frames, they analyze them all together, they compress them together, and you can get a very low bandwidth utilization this way. Example of these kinds of codecs is H.264 and HEVC. The problem with this, though, is so while it is useful and it compresses into relatively small signal bandwidth that can fit into a 1G and can be on the same network as the IT, it comes with compromises. Because it takes several frames at once and analyzes it together, automatically now you're creating a latency that is many, many, many frames. So these solutions, these kinds of codecs, always will generate a latency that is measured in hundreds of milliseconds. Now, for some applications, this is not an issue. But when you are dealing with an application, user interaction with a remote computer, live stager, just voice and video chat over network, this is not the right way to go because latency starts to be too high. So these are the two types of codecs, but there is a third one. And this is the one that the SDVoE platform uses. Rather than encoding one and compress one frame at a time or taking together multiple frames and compress them together, the pixel pipeline codec only works with few lines at a time. Takes in few lines, encodes them, sends out. By doing this, you are eliminating almost the latency in the system. The latency now is measured in microseconds. So now you have a latency that matches what your experience you have with the standard matrix switch. This codec was designed from the ground up to work on a 10 gigabit network pipe. It was in such a way that it only compresses when it has to, and there's always guarantee here, it always makes sure that there is at least 1 gigabit or more available bandwidth still for the IT network. So the consequences of putting everything on 1G means that you get a compromised performance. Compare this to the matrix switch, you have all kinds of compromises. Because you have to take the video signal and compress it, you create latency, you affect quality, and on top of that, you are still consuming so much bandwidth that this becomes a dedicated infrastructure just for AV. You cannot put it on an existing IT 1G gigabit network. These have to be two separate systems. Anyone claiming 12 to 1 compression without latency is really not telling you the truth. So imagine you go and talk to a network administrator who has a functional 1 gigabit enterprise network. And you will have this conversation with them about, I want to put dozens of transmitters on your network, each consuming hundreds of megabits. What do you think he's going to say? He's not going to say yes, because he knows that this will destroy his IT network. Of course, you can make some kind of compromises. You can try to take a use of quality of service, for example, and try to prioritize AV or IT, or AV over IT, or vice versa. But you always have to make this choice. And you always are going to have to sacrifice one or the other. Good experience for the AV user, the IT network, you're copying your file, and it just takes forever. Or vice versa. You optimize it for IT, and now your AV experience is shot. Everybody knows this today. The end user knows this, the AV integrator knows this. So what they do now with this current 1 gigabit AV distribution solution is that right from the get-go, they start planning for 2 different infrastructures. But that means 2 infrastructures to maintain, to control, of course to design, and all this promised cost savings that manufacturer 1G AV distribution solution promise you is out the window in the long term because it's just become more costly to manage long term. The solution really is already there. This is about, it's in order to have AV and IT converged on the same infrastructure and have the experience of the AV distribution system the same as we are all used to from the matrix switch, there's no other choice than increase the network capacity. And that means 10 gigabit network infrastructure. Using SDVoE, where the bandwidth uses up a lot of this 10 gigabit bandwidth, but always make sure that there's 1 gigabit or more left for the IT user. You now have AV users and IT users on a converged network, not stepping on each other's toes. Each can be doing their own thing, and because there is no very little compression on the video to begin with, you are getting what you're used to from the matrix switch. No latency, flawless quality. Yes and no. If I just compare, okay, I say 80 endpoints are going to install it. 10 gigabit endpoints, SDVoE types of endpoints, or 1 gigabit endpoints. The endpoints themselves is very similar in price. The difference is going to be the cost of the network switches. $8,000 is what I state here for an 80 endpoints AV system. $8,000? No, that can't be true. Well, that's the price of that switch behind you with 10 slots, 80 ports total, $8,000. So yes, 10G is a little bit more expensive. In this case, 2.5% more expensive. But which one is future-proof? Which one will cost you more long-term? 1 infrastructure versus 2 independent infrastructure. Performance all the time versus compromises that you never know exactly when will affect you. But isn't 10G complex? Any AV over IP system can be complex. It doesn't matter if it is 1 gigabit or 10 gigabit. This is the same Ethernet technology. All the same management techniques of network applies, regardless if it's 1G or 10G. The only difference is, on one G you're managing hundreds of megabits, and on the other one you're managing several gigabits. It's just, the only difference is the size of the pipe. Furthermore, the SDVoE platform has the simplest demand of any AV over IP system. It's very simple to set this up. You have to just enable few minor things on the network switch. And actually, when it comes from netgear switches, for example, the M4300 series, like the one over there, is already configured out of the box to work with SDVoE endpoints. IGMP is enabled, IGMP snooping is enabled, fast leave is enabled, and it will make sure that any unregistered multicast traffic doesn't go to all endpoints. But isn't 10G rare? I mean, no one has 10 gigabit infrastructure. Not true. A survey that Network did last year, they did a market survey last year. And they found out that among the small to medium-sized businesses, that is 500 employees or less, 33%, a third, already had 10 gigabit network infrastructure. Furthermore, 75% of those same enterprises were planning to have 10 gigabit network infrastructure in their premise by end of last year. So the chance is that now when you're bringing in an SDVoE platform living on a 10 gigabit network, and you want to have it converged with IT, the chance is that that 10 gigabit network infrastructure already exists. You just maybe have to expand it a little bit to add few ports to hook up your endpoints. And then it is the investment. When you invest long term, you want to invest in something that is future proof. You have a choice, of course. You can decide to invest in a dedicated matrix switch. Works great, no latency, flawless quality all the time, determined performance, deterministic performance. But the HDMI, there will be the next version of HDMI and you are going to have to rip that out and replace it with something new. You can decide to instead invest in dedicated 1 gigabit network. But why would you do that? If you start with 1G, because we have all those compromises, you would actually be better just to stick with your existing matrix switch. And actually, it's likely, we know that IT is there are already bottlenecks in 1 gigabit networks in the enterprise today. The likelihood is that 1 gigabit is not going to be even enough in 2 years from now for just IT use. And then forget about converged IT and AV distribution. Invest in 10 gigabit infrastructure. If you don't have it already, you're future-proofing your system. And you now know that you have the bandwidth required to have the matrix switch performance on a network that is converged with your IT. So what to choose? HEVC, great choice when your network bandwidth is limited. Wireless. Getting the data to your smartphone, to your tablet, or with wireless links, where bandwidth is limited to begin with. Because this is such an efficient encoding. Very low bandwidth. You can also consider it's also perhaps a compromise for you if latency does not matter for your application. If it doesn't matter if the latency is 0 seconds or 1 second or 5 seconds, it doesn't matter to you, then maybe this is the right way for you to go. What I can tell though for sure is the Intraframe codecs, like the MJPEG 2000, they don't make any sense at all. They're just bad overall. The compromises just that you have just make no sense. You end up with visible problem with quality. You have noticeable latency. And for what? Because it still consumes hundreds of megabits, it forces you to build an independent infrastructure. Crestron NVX is one of those endpoints that take use of this kind of a codec. If you go and look up their spec sheet, which is available online, they will tell you that these endpoints can consume up to 990 megabits per second. You have 10 megabits left for something else. And since this now forces you to build a dedicated infrastructure, why not just use matrix switch or point-to-point extensions instead? The SDVoE Pixel pipeline is really the best choice when it comes to pro AV signal management. There's zero latency, there's flawless quality, and remember, video demands are going up, not down. We are 4K today. We are now in the middle of talking about HDR, better pixels. That increases the bandwidth because there's more pixel depth in the signal. And then we're talking about 8K. So the bandwidth is the one thing that follows the Moore's law and is cheap already and getting cheaper. You cannot say the same thing for latency and quality. They don't ride the same Moore law. Latency is your time and becomes very critical for all applications where you are interacting directly with another computer, remote desktop, virtualization, or a live camera. So when it comes to making this trade-off between bandwidth, low latency, and high quality, make sure you're making the right compromise. So I want to thank you all. Thank you so much.